Hey everyone, welcome back, and today let's solve Leetcode problem 2845 titled Count of Interesting Subarrays. So we're given a zero-indexed integer array nums, an integer modulo, and an integer k, and our task is to find the count of subarrays that are interesting. And a subarray nums from index L up until index R is considered to be interesting if the following condition holds. Let count be the number of indices I in the range of indices in that subarray from L to R, such that nums at I modulo or kind of modded by our modulo input integer is equal to the k value. If that's the case, then count modded by modulo also has to be equal to k. We want to return an integer denoting the count of the number of interesting subarrays that have this property, where again it quickly defines the subarray to be a contiguous non-empty sequence of elements or indices within an array. So in example 1, we have our input array nums to be 3, 2, 4, and our modulo and k values to be 2 and 1, and we have 3 as our output because we have 3 different subarrays that are, well, interesting. And those interesting 3 different subarrays are actually listed down here in the explanation. So I'm just going to quickly gloss over this, nothing to worry about too much. So the first subarray is nums at index 0 up until index 0. That really is just one index of index 0, and that's going to be the singular initial element or index 0 element 3. Notice how there is only one index in the range from 0 to 0 that satisfies that condition, where 3 by modulo it gives us a value of k1, because 3 modded by 2 does indeed give us a value of 1, which is indeed our k value. So count equals 1 is, satisfied, and because count modded by the modulo is equal to k, right? The next subarray we have is from nums from index 0 up until index 1. That would be this 3 and this 2, right? There still only is one index I equals 0 in that range. That satisfies the condition where 3 modded by 2 is equal to 1. So count would still be 1, as count modded by modulo is equal to k. Right, and applying this logic from nums from index 0 up until index 2, it is also still considered to be a valid interesting subarray, 3, 2, 4. So we have 3, 3, 2, and 3, 2, 4, and there are no other interesting subarrays. There's only 3 interesting ones. And example 2, applying that same logic here, we have actually only 2 interesting subarrays, and those would be 3, 1, 9, 6, and those would be the singular element 1 at index 1, right? That actually have that property of nums that I be modded by modulo having a mod of k. So for the constraints here, we see that the length of our input array nums is going to always be between 1 and 10 to the 5th power, and the value in our modulo value itself are also always going to be between 1 and 10 to the 9th power, and our k value is always, of course, going to be less than modulo, but still greater than or equal to k, basically meaning that it's not going to be, or never going to be, it's never going to be negative, right? Let's go ahead and get into the main observations that we really need to make to solve this problem. And the main one is that, well, checking every single possible subarray is definitely, a brute force and valid approach, but it's very inefficient. Why? Because of course we know we need nested loops for that. That goes to n squared, and clearly n squared is not going to work for the solution because our length of input array nums can go up until 10 to the 5th power, and that's just going to give us a very, very simple TLE, right? So we need to actually optimize that kind of approach there, and to do that we'll actually use another very common algorithm called the prefix sum, right? Prefix sum, as the name suggests, we're going to be keeping track of the count of elements satisfying the condition up until each index that we iterate over, right? So from the beginning up until each index that we iterate over the input array nums for, hence the name prefix. It's the first x elements up until some index x in each iteration as we iterate through the input array nums, right? And to actually efficiently find the number of subarrays that end at a particular index that satisfy our condition, we can actually use a hash map or a dictionary like we used in yesterday's problem to actually store the frequency of prefix sums modulo by modulo, mapping to their frequency in the hash map. Right? So how are we going to solve this problem at a high level? After we actually initialize our hash map to store the frequency of prefix sums, we'll actually start with a base case or starting values of 0 to 1, because why? Well, of course, for all subarrays that start and end at, or rather, for all the subarrays that start at index 0, of course, there's only one of them, and so 0 is going to be mapped to 1, right? And we're going to iterate through the array, and we're going to update that prefix sum count as we iterate through the array whenever we actually encounter an element that satisfies the condition of nums at I being modulo by modulo equaling a k value. And at each step, we always have to calculate the target value that when we actually subtract it from the current prefix sum modulo or modded by modulo, it has to always give us k, because that's kind of like our target value to get a valid element. And if the target actually exists in the hash map so far, we know we can add its frequency to the answer and increment that accordingly. So let's go ahead and get into the code here. So like I just talked about, let's actually initialize our hash map first. I'm really just going to straightforwardly call it count, because that's really the whole point of it. It's literally keeping track of the count or frequency of all the different prefix sums that we found that are modded by modulo. And so it's going to be actually initialized to a default dictionary with our default data type or parameter being integer, right? Basically just every single key has a default value pair, so we don't have to check for any values that we haven't seen before. Now for the actual base case here, we kind of talked about this as well. Count at 0 is always going to be being mapped to 1. Why? Because the initial state where the prefix sum is 0 is obviously going to have only one possible thing at index 0, right? So now let's actually initialize our prefix sum, that is. Of course, that's also going to be initialized to 0. That's going to basically be the running counts of elements that actually satisfy nums at index I modded by modulo equaling k. And finally, we're going to get our result. And this is, of course, our output. This is, of course, what we want to actually return, our total number of interesting subarrays that we find throughout the entire array. So now that we've actually initialized these integer variables, now let's actually start iterating through the input array nums and checking for these valid subarrays and valid elements that actually have modded modulos equal to k, right? So for every single number or element in the input array nums, basically a very simple, straightforward iteration. If the current element num modded by modulo, what do we want? I think this should be an O, modulo, yeah. What do we want num modded by modulo to be? Well, like the problem states, we want it to be equal to k. So if it is equal to k, we of course want to increment our prefix by 1. Why? Because we've actually seen one more valid element that has a kind of valid property of the current number being modded modulo to be equal to k, right? It's one more valid element because, again, recall that prefix is nothing but storing the count of the elements that satisfy the condition, right? Now, if we actually do find that element, we'll then increment our prefix count, and then we want to actually calculate this key as prefix minus k modded by modulo. That's kind of like the number of times we've seen that prefix sum to make the current subarray interesting. So I'm going to call it key, and it's going to be prefix minus our k value, and this is going to be modded by, you guessed it, modulo. Right? Sorry. So prefixes, again, the number of kind of valid elements or elements that have that property that we've seen so far. That's going to be subtracted by our k value, and the result is going to be modded by modulo, right? It's going to represent the number of times that we've seen a prefix sum that would make the current subarray interesting, right? And now let's actually add to our results, so result plus equals the corresponding value of count at that key. The key is, again, okay, yeah. Now that I've unindented that, we're going to add count at the key value right here, because we have to actually add the frequency of that kind of target key in our count dictionary to our result, or whatever the key value is at that iteration. It could be a default value of 0. It could be something else. And finally, we then have to actually update our count dictionary with the current prefix and the current prefix modded by modulo and its corresponding result, and increment that value by 1, because of course we've seen it one more time in this current iteration with the current number prefix, right? So we'll get count, and we'll get it at the key of prefix modded by modulo, so prefix modded by modulo, and we're going to increment its frequency by 1 because of course we've seen it one more time. We've seen the value of prefix modded by modulo one more time with this current element in this current iteration. And effectively, once we actually do that for every single element in the input array nums, once this for loop is actually done executing, once it fully terminates, we've iterated through all the elements in the input array nums, we're going to return our result, because eventually it would have actually stored the total number of interesting subarrays throughout the entire input array nums with that property that we see in the problem statement above. So unless I made any syntax errors here, this should be accepted and there should be a valid solution. So let's go ahead and double check that. Okay, sorry, looks like I completely forgot to initialize my result. This should of course be initialized to 0. So now let's go ahead and double check that and see if it works. Hang tight, and as you can see, this really is just about as efficient as you can get it to be. So on a high level, again, what are we really doing here to solve this problem in the most efficient way possible? Well, effectively, we're keeping track of the count of the qualifying elements, or the valid elements, if you will, using that prefix sum idea, and we're also using that extra hash map count to actually store the frequency of the prefix sums modulo by modded, or modded by modulo. And at each index or iteration, we always determine how many previous prefix sums would also form an interesting subarray with the current prefix sum, kind of like that target value, where we always consider all the valid subarrays without actually explicitly checking each one in the brute force nested loop solution, making our solution, of course, a lot more efficient, which brings us to the complexities of this solution. So for the runtime complexity here, Very straightforward. Instead of big O of n squared, we simplified it or optimized it to big O of n, or linear time, where n is of course the length of our input array nums. Why? Because this really is just a singular pass one for loop solution where we iterate through the array exactly once. And of course all these little operations are done in constant time. They're not going to affect our runtime complexity, and so on average we're going to have a linear or big O of n runtime complexity, and for our memory or space complexity it's going to be actually big O of modulo. The reason why is because our count dictionary would store at most modulo different keys from 0 to modulo -1, and so it's going to be big O of modulo for the memory or space complexity. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye bye.